All right. Thank you for the introduction. I'm Michelle Wong, and I'm a PhD student at the University of Toronto, studying with my advisor, Professor David Lee. And our paper is on a new type of obfuscation that we're seeing in Android malware, and the tool that we've developed to try to detect and deobfuscate these techniques. So there's been a large body of research in mobile security into the development of analysis and detection tools for Android malware. And in response to the scrutiny, malware developers, of course, try to hide the actions that their applications take so that these applications don't get flagged as malware. And they generally do this by using code obfuscation techniques to defeat code analysis. We've seen obfuscation in x86 malware. On mobile and on Android devices, the obfuscation techniques that are used manifest a little bit differently, since most applications are implemented in Java, compiled into a DEX bytecode format, and then executed on a custom runtime on the Android device. Previous work into Android deobfuscation has mostly looked into how the application's Java or DEX bytecode tries to hide itself from analysis. And this included techniques like using reflection, dynamic code loading, or hiding specific functionality in native code and invoking it using the Java Native Interface, or JNI, since a lot of existing security tools are limited to Java code analysis. In this work, we refer to these techniques as language-based obfuscation, since they work by making use of features of the Java programming language. And the use of these features, such as specific APIs, is detectable in the bytecode and or detectable by an analyzer, but not always resolvable without some form of runtime information about the application. On the other hand, an application could try to hide itself as much as possible by implementing it by having it implemented entirely in native code, bypassing the Java runtime and any sort of Java code analysis. And to do this, there can be no invocations to Java methods of any kind. We call this full native code obfuscation, and theoretically, they could also use existing x86 obfuscation techniques to hide itself even more. While this is a very effective way of performing Android application obfuscation, we don't really find a lot of examples of malware that do this. And we believe this is because most of the interesting sensitive functionality on an Android device that a malware developer would want to abuse is provided by system services and accessible through the Android framework and the APIs it provides. However, the framework and the APIs are mostly implemented in Java. So a full native code application that would want to access this functionality generally has to bypass the framework and access either low-level or undocumented interfaces of the system services themselves, making these applications more difficult to implement and more susceptible to compatibility loss if these interfaces should change. In this work, we were interested in whether other types of obfuscation was possible for Android applications, and specifically whether there was a middle ground between language-based obfuscation, which is fairly easy to use but also easy to deobfuscate, versus full native code obfuscation, which is effective but makes it difficult to access that sensitive Android functionality. And in our investigation of recent Android malware, we found that this middle ground does exist. And applications do this by tampering or modifying the runtime that's actually executing its Java or DEX bytecode. We looked at these techniques and called them runtime-based obfuscation, and it essentially allows an application to sort of declare that they're doing one thing when really doing something else under the covers. So the way runtime-based obfuscation usually works is that the application will load or initialize the runtime with some DEX file that seems fairly innocuous and would probably get flagged as benign by an analyzer. However, the application also has a separate component that's not necessarily malicious per se, but it's definitely in a gray area in that it changes values in the runtime that applications normally wouldn't access. And the results of these changes is that, for instance, the runtime may think that it's loading a class from this benign DEX file, when really it's loading a class from a different source of bytecode. Similarly, the runtime may think it's invoking one method when really it's invoking another, or it's executing instructions for some benign method when really it's executing instructions from some different source. And the benefits of doing this runtime tampering to achieve obfuscation is that while the tampering or modification of runtime state has to be done in native code due to the memory management restrictions in Java, the actual obfuscated or hidden code that's executed as a result is implemented in Java, meaning that malicious code that's obfuscated in this way has easy access to those framework APIs and the functionality they provide. So to look at how exactly this unexpected code behavior is possible, we investigated the code loading and code execution processes within the Android runtime, or ART, and identified several ways where the application can modify this runtime state. So looking first into the code loading process, when the application wants to load a file of bytecode into the runtime, ART will first map this file into memory, and it also creates objects that keeps track of the metadata for this file. There is a Java text file object that allows Java code to reference this file later, and it contains a pointer to a native text file object that will track where this file and where this bytecode was loaded into memory. And we found that one type of runtime-based obfuscation can happen here if the pointers in these objects are modified so that they either point to different text file objects or a different location in memory where the application has secretly loaded other bytecode. We call this text file hooking because it essentially the original text file that should have been loaded into the runtime has been swapped out for another one. Also, if the application knows where this file was loaded into memory, it could also overwrite the contents at that location so that the file might now contain malicious code. And we call this bytecode overwriting. If the application can time this hooking or overwriting so that it happens after the file has been loaded into memory, but before ART parses it to create classes and method objects, this can essentially lead to the execution of unexpected class and methods from this file. Next, we looked into the code execution process where these classes and methods are used after they've been loaded. And execution happens when the application makes a method invocation. Assuming a virtual invocation, before ART can actually execute anything, it has to first resolve which method or overridden method it should be using. And it does this by looking up the type or the class of the receiver object for the invoke statement and indexing into its virtual method table to retrieve this ART method object that it'll then execute. And we found that another type of runtime-based obfuscation can happen if the pointers in this virtual method table are modified so that an unexpected ART method object is returned and executed. And we call this ART method hooking. Finally, after the method resolution process has returned some method, execution happens in ART by looking up an entry point, which keeps track of how this method should be executed for the current configuration of the runtime. And essentially, this entry point code will grab a code pointer that it should be using and then execute the instructions that are found there. And we found that obfuscation can also happen here if the entry points are hooked so that arbitrary code gets executed when the method is invoked. And obfuscation can also happen if these code pointers are hooked or the contents that they point to modified so that unexpected instructions get executed even though a seemingly benign method might be being invoked. And overall, we've identified 6 specific ways where runtime state can be modified by the application in this way to achieve unexpected and likely malicious code behavior, even though it looks like benign code was initialized or loaded into the runtime. And this isn't an exhaustive list of all the different types of runtime-based obfuscation that's possible. The ones we've identified here do touch different parts of the code loading and code execution processes within ART, and we have found examples of them in recent Android malware. So, of course, the next step is to try and detect and deobfuscate these techniques. And our ultimate goal was to have a unified framework that can handle older language-based techniques as well as these newer and more complex runtime-based obfuscation. In our design, we found that pure static analysis was generally insufficient for deobfuscation since we really do need runtime information about what the application has loaded and executed. But pure dynamic analysis often suffers from a lack of code coverage since you can't analyze a piece of code without first executing it. And this would mean trying to execute all of the paths or possibly obfuscated paths in an application, which might not always be feasible. We turned to the idea of targeted execution, which is something we've used in the past. And the idea behind targeted execution is that when we're performing security analysis, a lot of the times we're interested in whether an application performs some interesting behavior. And more often than not, this interesting behavior only happens in a small part of the application's code. Therefore, trying to execute all of the paths in an application dynamically can be a bit of a wasted effort with respect to that security analysis we're trying to perform. So in targeted execution, we take a hybrid approach, where we use static analysis to identify potential interesting behaviors and extract the paths to them. From those paths, we extract constraints that we then solve to generate inputs to inject. And on the dynamic side, we're more efficient since we're only injecting inputs and triggering call paths that can lead to potential interesting behavior that we want to analyze. Of course, for obfuscated applications, there's a problem in that the static analysis might be incomplete and some of these execution flows might be missing from our model. So we address this by passing dynamic information back into static analysis to try and resolve these flows. In this scenario, the interesting behavior that we would want to target and analyze dynamically are then the locations where obfuscation might be occurring in the application. So we took this idea and designed and implemented Tiro, a hybrid iterative deobfuscator for Android applications. Tiro stands for the 4 steps: target, instrument, run, and observe. And it's based on the idea of having static analysis identify obfuscation locations and triggering them, and then using dynamic analysis to gather information that can help us deobfuscate those locations. The input should be a compiled APK file, and after several iterations, Tiro should produce a deobfuscated application that we can then pass to other tools to improve the effectiveness or completeness of their analysis. And to show the 4 steps of Tiro, this is a reflection example where the name of the method being invoked reflectively is obfuscated by this decryption routine. And in the first targeting step, Tiro will first identify obfuscation locations, which in this case is the reflection API invocation, and it'll extract the call path and constraints from onCreate to method.invoke. In the instrument step, it'll instrument this location to report values that it needs for deobfuscation, which in this case is the name of the method. In the dynamic run step, it'll take the previous targeting information and generate inputs that will trigger this path from onCreate to method.invoke. And as it executes this path, the instrumentation will log that the reflection in this method at this location can result in this foo method being invoked. And in the observe phase, Tiro will take this information and model the flow from onCreate to foo. So reflection is a rather simple form of language-based obfuscation. But Tiro can use the same 4 steps to handle the more complex runtime-based obfuscation I've described previously. And it does this by taking advantage of the knowledge that to modify runtime state, the application has to use native code to do this modification. So before obfuscation happens, there has to be some Java to native code transition. However, the obfuscation isn't actually complete until this obfuscated code is executed, and this obfuscated code is implemented in Java. So there also has to be a native to Java code transition after this tampering is done. So for Tiro, we take advantage of this by checking for changes in runtime state before and after application native code is executed. So to show how this works, this is a different example where a native method called native foo is being invoked, followed by a normal Java method called bar. And so when Tiro sees this code, it'll first target this invocation to native foo, since it'll treat all application native code as a possible source of obfuscation. In the instrument step, Tiro uses an instrumented art runtime that checks for changes in runtime state on these Java to native and native to Java code transitions. And in this case, we're interested in the runtime state for the bar method. And when native foo executes, it changes the state so that the code pointer for bar now points to a different sequence of instructions that will get executed. When Tiro runs this code and triggers that path to native foo, this instrumentation will log that in the onCreate method, at the location where native foo is returning back into Java code, the code pointer for bar has been modified, and it'll extract this new bytecode for the bar method. And finally, we model this new bytecode with a synthetic method, and then model the flow from onCreate to this new method. And since Tiro is iterative, this runtime information can be passed back into static analysis. So in a subsequent targeting step, Tiro will see that this invocation to bar can lead to this new bytecode being executed. So it'll also look for locations of obfuscation in this new bytecode and then deobfuscate them using the same 4 steps. For the implementation, we use the sub framework for the static component to do the analysis and instrumentation of application code. On the dynamic side, we use a modified version of AOSP that contains our instrumented art runtime that does this runtime state monitoring. We also have a separate process that parses our deobfuscation log and extracts any dynamically loaded or modified bytecode from our testing device. For our evaluation, we first want to look at Tiro's abilities to detect and deobfuscate techniques used in modern Android malware. And we also want to look at how different obfuscation techniques were being used by malware in the wild. And finally, we provide an evaluation of Tiro's performance in our paper. So looking first into Tiro's deobfuscation capabilities, we evaluated Tiro on a dataset of obfuscated malware samples that was provided to us from the Android security team at Google. And this dataset was manually labeled by the obfuscator or packer that was likely used on the original application. And these are listed on the left. This is a subset of the interesting results we had, and our paper has the full results of the 22 obfuscators we evaluated on. We found that all of the samples did some form of language-based obfuscation. For runtime-based obfuscation, we looked for changes or tampering of runtime state in DEX bytecode, DEX file objects, and class and method objects. And we found that 53% of the samples did some form of runtime-based obfuscation. A lot of the tampering of runtime state was done on a larger scale, where entire DEX files were being hooked or swapped in, although we did find cases of more fine-grained obfuscation where method or instruction pointers were being modified. To deobfuscate these applications, Tiro took on average 2.3 iterations, with all of the samples requiring more than 1 iteration because of the combination of obfuscation techniques they used. And finally, we want to look at how Tiro's results could potentially be used. And we looked at the sensitive API invocations that could be detected statically before and after running Tiro, where the sensitive APIs are the list of sensitive sources and sinks from the FlowJoy tool. And we found that on average, we were able to detect over 30 new uses of sensitive APIs per application, showing that by using these deobfuscation results, we can get a better view of the actions and potential malicious behavior in an application. Next, we wanted to look at how different obfuscation techniques might be used by malware in the wild. And we ran Tiro on a data set of 2,000 obfuscated malware samples from VirusTotal. Once again, we found that most of the samples did some form of language-based obfuscation. And for runtime-based obfuscation, we found that 80% of them did some form of runtime-based technique. This is a much larger percentage of runtime-based obfuscation usage than in our previous data set. And we believe this might be because this VirusTotal data set is slightly newer and might contain more sophisticated obfuscation techniques. So to conclude, in this work, we show a new type of obfuscation techniques in Android that hasn't really been reported before. We categorize these techniques and call them runtime-based obfuscation because of the way they tamper with runtime state to achieve this unexpected code behavior. We also present Tiro, a hybrid iterative deobfuscation framework that can handle older obfuscation techniques as well as these newer runtime-based ones. We show that Tiro is able to deobfuscate modern malware and uncover new sensitive behaviors in these applications. And we also show that runtime-based obfuscation is already in use in malware today, with 80% of the samples from our VirusTotal dataset doing some form of runtime-based obfuscation. This is our contact information if you're interested in our work, and we have put some of the code for Tiro up on GitHub. Thank you for your attention.
Okay, thank you. And we have time for some questions.
Hello, this is Renimeo from Google. If I understand correctly, the additional sensitive API calls that you found, they were already in some Java class. So did you find them because you found the new paths on how to invoke them, or were those sensitive API calls themselves obfuscated through native invocations?
Some of them were obfuscated through native invocations, so native code invoking those methods.
Yeah.
Some of them were in these sort of dynamically loaded or modified bytecode that resulted from runtime-based obfuscation.
But that was originally loaded from another Java file, just hooked into the control flow through native.
Yeah, some of them were in they were like called from Java code that's being hooked that way.
The API calls they are already in Java code, but a static analyzer wouldn't have seen them being invoked.
Yeah.
Okay, thank you.
I also have a question. So, what if an attacker is aware of your methods? So, what are the limitations? How could he bypass the analysis steps?
Right. So our monitoring of runtime state is done in the runtime. So and it's done in native code. So the same runtime-based techniques can't bypass them, but native code obfuscation techniques could try and hook some of the methods we use. So this is a limitation for us. And it's sort of the same limitation as why runtime-based obfuscation is possible, in the sense that the runtime and the application is in the same memory space, and there's no protection there.
And the second question is related to the dataset. So you mentioned in your talk that the 2,000 samples from VirusTotal, they were obfuscated, or did you just randomly download Android samples?
They were obfuscated, yeah.
How did you determine that they obfuscated?
I believe we use obfuscated as a keyword. Yeah.
Okay, so if there are no more questions, then let's thank Michelle again and